Hey everybody, today we're going to be working on day 2 of our graph sketching. And so in the first day, if you recall back, we were just working with the first derivative, and that was giving us information about our critical points and where a function is increasing or decreasing. So today we're going to pick up from there, and we're really going to be focusing on the second derivative and what that tells us about a function. And at the end of the video, we'll pull it all together. So the first kind of new vocabulary word we have for today is called points of inflection. And so points of inflection are places, this should say where, the second derivative, y double prime, is equal to 0, or where it's undefined. Now, actually finding where it's 0 or undefined gives us possible points of inflection. To know if it's truly a point of inflection, we have to know that the derivative changes sign at that value. And so we'll talk about that a little bit more here in this example. So now, there's really two ways that this question could be posed. Option one is if they give you f of x, so the actual function. So here we have a function f of x. It probably looks familiar by now. And we're going to be finding the points of inflection. So here we go. I know if I'm finding points of inflection, I need to get down to that second derivative. So here's my first, 8x cubed minus 8x. And then my second derivative is going to be 24x squared minus 8. And I'm going to look for where that's equal to 0. Since it's a polynomial function, I know it's not going to be undefined anywhere, so I'm just focusing on where it's equal to 0. Now, this isn't going to give us a real nice number, but that's okay. Let's see, 24x squared is equal to 8. So x squared is 1/3. So then x is plus or minus 1 over root 3. So I have two possible points of inflection. Now again, with critical points, we could just take those x values and call them our critical points. But here we said they're only points of inflection if the derivative changes sign. So I need to do a quick check to make sure that's actually the case. So I'm going to do a number line here to test if my function is changing, or my second derivative is changing signs. So I have negative infinity, I've got negative 1 over root 3, I've got positive 1 over root 3, and then I've got infinity here. Now, I know this is kind of a funky number that we're not used to working with, so if you pop that into your calculator, let's see. We would see that that number is approximately negative 0.577. So just to help us out, I'm going to make a note. So that'll help us picking out points to fill into our number line there. So if I want something between that negative number and negative infinity, I could just pick negative 1. If I plug that back into my second derivative, a negative 1 squared is just going to be positive, so 24 minus 8 is going to give me a positive value. Now I want to pick a number in between, so 0 is an easy choice. If I plug that in, my second derivative is going to be negative. And now I'm going to plug in something bigger than that. I should have put plus or minus here. So I'm just going to pick 1. So again, if I plug in 1 to my second derivative, it's positive. So now that I can see at both of those values, my second derivative actually changed signs. In this case, from positive to negative. This case, from negative to positive. So I do truly then have 2 points of inflection. Now, we could also be asked to find this information if we have the graph of f prime. Remember, if I'm looking at f prime, I know I have points of inflection is equal to 0. So that means on f prime, I'm looking at horizontal tangents. Ooh. Okay. Now, I'm not going to be able to pick off those exact values very nicely, but I see that occurs here, and that's going to occur down here. And now, we said this was about positive or negative 0.577, and so it does seem that that matches what's happening here in the graph. Okay, so now we need to know what those points of inflection help us find. And that is going to tell us all about the concavity of the function. And here's what I mean by that. We say that a graph is concave up if it has a behavior like this. So we say it's concave up like a cup, or it could hold liquid. Concave down, we say it's more like a frown, so it would dump anything that we tried to put in it. So now, this relates to second derivatives. We know if it's concave up, if my second derivative is greater than 0, and we're concave down if we're less than 0, if that second derivative is less than 0. Now, we actually did a lot of this work already. So if I have f of x, again, my function is the same one we had up here. Now we're just being asked to determine where the function is concave up and concave down. What we would typically do is solve for where it's 0 and then test our number line to see the changes in sign. Since we already did that work here, we only need to do one part now. We know that we're going to be concave up wherever the second derivative is positive. So I have two intervals where that's happening. From negative infinity to negative 1 over root 3. And then again from 1 over root 3 to infinity. And again, since it's a second derivative, we use open intervals. Now I am concave down in between negative 1 over root 3 and 1 over root 3. My second option for finding out about concavity is looking at the graph of f prime of x. Okay, we know that we're going to be concave up where f double prime of x is greater than 0, which means that the slope of f prime is greater than 0 or positive. So my slope of f prime is positive over this interval, which we know corresponds to negative infinity to negative 1 over root 3. And I also have a positive slope here from 1 over root 3 to infinity. I'll be concave down where f double prime of x is less than 0, which means the slope of f prime is less than 0. And we can easily see we just have one interval where that's happening, which is here between negative 1 over root 3 and 1 over root 3. Sorry, that's kind of jammed at the bottom there. All right, so now we're going to take what we know about the first and second derivatives and pull this all together. So in the examples we look at, we're going to be finding out where the critical points, the points of inflection are, where we're increasing, decreasing, concave up, and concave down. So our first example, we're going to work with the actual equation here. So first thing I need to figure out is everything related to my first derivative. So negative 3x squared plus 6x, and I want to know where that's equal to 0. So I'm going to factor out a negative 3x, which gives me x minus 2. So I have critical points at 0 and 2. So I'm going to go ahead and fill those in. Now I'm going to go ahead and find my second derivative. So negative 6x plus 6. Again, I'm going to find where that's equal to 0. So if I factor out a negative 6, I have x minus 1. And so now I have x equals 1, but I'm going to make myself a note here. At this point, that's just a possible point of inflection. I haven't verified that the second derivative actually changes sign there, so I don't want to include it yet as a point of inflection. So let's go ahead and build our table here. I have y prime and I have y double prime now. And I don't have a specified interval, so I'm going to be going from negative infinity to infinity. So let's see, I have a critical point at 0, a possible point of inflection at 1, another critical point at 2, and then I'm going to put infinity at the end here. So let's see what's happening. I'm just going to test my first derivative for right now. So my critical points are 0 and 2. So I'm going to pick a point to the left of 0, let's say -1. If I plug that in, I'm going to have a positive times a negative, so I'll have a negative value here. Now, my next critical point is 2, so I only need to test one point in between 0 and 2. So 1 seems like a good point in between. So if I plug in a 1, I have a negative times a negative. That's going to be positive. So I'm going to be positive everywhere between 0 and 2. That's why I can fill in both of those boxes. And then something greater than 2, let's pick 3. It's going to give us a negative times a positive, which is a negative. So now at this point, I can fill in. I know I'm increasing where my first derivative is positive, so from 0 to 2. And I'm decreasing where it's negative. So negative infinity to 0 and 2 to infinity. All right, now let's look at our second derivative here. So my only possible point of inflection is here at 1. So I only need to test 1 point less than 1 and then 1 point greater than 1 to fill in my table. So less than 1, let's plug in 0. I can see that's going to be positive. So everything less than 1 gets a positive. If I plug in something greater than 1, let's say 2, I'm going to have a negative. So everything greater than 1 gets a negative. So now I can see that at 1, I did change signs from positive to negative. So that means I have a point of inflection at x equals 1. I'm going to be concave up everywhere my second derivative is positive, so from negative infinity to 1. And I'm concave down where that derivative is negative, so from 1 to infinity. All right, last part here now is looking at f prime to answer these same kinds of questions. So we'll start with critical points. Again, that's where we know f prime equals 0 or undefined. So in this case, we don't have any corners, cusps, or discontinuities, so we don't have to worry about this second piece. So I'm only looking where f prime is equal to 0. Again, this is f prime, so I'm focused on the zeros of that function, which happen at -4, 0, and 4. Increasing, I know, is where f prime is greater than or equal to 0. So I'm talking about above the x-axis here. So negative infinity to -4. Oops, excuse me, that should be closed because it's first derivative. And then I'm above the x-axis again between 0 and 4. Decreasing is just the opposite. So I'm looking below the x-axis. That's going to happen here from -4 to 0. And then again at this tail end from 4 to infinity. Okay, now points of inflection. Actually, let's look at our concavity first, and then we'll know that point of inflection will occur where I have a change in concavity. So concave up, we said, is where f double prime is greater than 0. Now, if I have f prime, to get f double prime, I know I'm looking at the slope. So this is where the slope of f prime is positive. Now, f prime has just one place where the slope is positive. That's going to be here from -2 to 2. And again, I'm working with an open interval here because that's a second derivative. Concave down, again, is just where double prime is less than 0. So I'm looking for where the slope of f prime is negative. I can see that's happening here. Negative slope from negative infinity to -2. And again, from 2 to infinity. So now, I do have some points of inflection, right? I know that my concavity changed at -2 and at 2. And again, that makes sense. We said this should be wherever my second derivative is 0. At both of those spots, I have horizontal tangents, so the slope at those points is 0. Okay, so this has pulled together everything we know so far. And the next couple of days then as we go forward, we'll be looking at really talking about some max and min values and other information we can get about these graphs so that ultimately, if we're given the function for an equation or the equation for a graph, we'll be able to actually sketch that graph. So that's it for today. I will see you tomorrow.